If you check the evening news during a heat wave, the weather forecast usually looks like this: a two-dimensional map covered in expanding red zones to show you exactly where the heat is hitting. Standard maps communicate the location of a heat wave, but they leave out a critical variable for human survival: duration. A brief weekend heat spike is a nuisance, but the record-shattering mega heat waves of 2003, 2019, and 2022 parked over Europe for weeks, causing a catastrophic loss of life. To solve the mystery of why extreme heat locks into place, meteorologists realized they had to look past the surface of these maps and start looking vertically into the sky. Viewing a heat wave as a three-dimensional, multi-layered structure provides the context necessary to determine if a region faces a brief hot spell or a persistent, life-threatening disaster. Researchers categorize these events into distinct vertical profiles. The higher tropospheric heat wave occurs exclusively in the atmosphere's top third. Despite intense heat, these short-lived events last 5 days at most. Struggling to reach the surface, the hot air mass dissipates quickly. The dynamic changes when high-altitude heat sinks toward the Earth, creating an omnipresent heat wave. As the air mass descends, atmospheric pressure forces it to compress. This compression bakes the air further through a process called adiabatic warming. There is also a lower tropospheric profile, where warm air is blown horizontally into the mid-levels of the atmosphere, similar to 2019, when hot Saharan air was pulled across Spain and into France. This chart compares the lifespan of these different events. The blue bars represent the short-lived high-altitude flashes, while the green and gray bars show that sinking and moving air masses survive much longer. While sinking air extends the life of a heat wave, atmospheric dynamics alone rarely lock a mega heat wave in place for multiple weeks. The most dangerous profile is the near-surface heat wave, which develops strictly at ground level. These events are defined by their persistence. They can suffocate a region for 15 to 17 agonizing days. One specific factor allows this profile to persist: severe drought, known as soil moisture preconditioning. Normally, damp soil uses solar energy to evaporate water, which carries heat away. Without that moisture, the sun's energy goes directly into baking the air at the surface. This superheated air deepens the atmospheric boundary layer, effectively trapping the heat and turning the landscape into a self-sustaining outdoor oven. The data shows a clear link between these long-duration events and dry Earth. These red lines track the longest heat waves, and almost all of them occur when soil moisture is depleted well below the 25th percentile. A catastrophic heat wave's ultimate lifespan is dictated by both the hot air arriving from above and the parched soil waiting below. Every extreme heat event acts as a complex, deeply interconnected three-dimensional engine. A modern perfect storm occurs when a high-altitude atmospheric anomaly locks over a landscape already ravaged by drought. Accelerating climate change is driving an increase in early summer droughts, which preconditions the ground to trigger these multi-week megaheat waves. Effective meteorological forecasting now requires tracking the three-dimensional architecture of the entire atmosphere, moving beyond the simple measurement of maximum ground temperatures. Understanding this vertical anatomy is our only reliable defense for predicting how long the heat will last, allowing cities to prepare before the oven door closes.